Hey boys and girls, as you remember from the last set of videos, we talked about oxidation numbers, and that's going to drastically relate into how things bond, how different atoms interact with each other. And realistically, when we talk about bonds, we're going to talk about how the oxidation numbers affect an element's stability. And really, our big example of that is going to be our noble gases. That's where we're going to start. Noble gases are the most stable elements. And the reason that they are so stable is because they have 8 valence electrons. Every atom wants to have a stable outer shell. We talked about that last set with the oxidation numbers, and to have 8 valence electrons. Okay, so noble gases are happy because they already have that 8 valence electrons, with the exception of helium, which has its 2, but it still has a full outer shell. Every other element, however, is striving to be like a noble gas, to have a stable outer energy level, to have its 8 valence electrons. In order to do that, other atoms are going to go through and gain or lose electrons to try to get to that magical number of 8 valence electrons. Okay, and a big key to point out here is that chemical bonds only involve electrons itself. The nucleus doesn't matter. I don't really care about the protons that are in the nucleus. I don't care about the neutrons that happen to be in the nucleus, because neither of those happen to be involved in the bonding patterns. They happen to be very, very, very important when we're talking about the mass and stability of an atom, and they happen to be important when we're talking about specifically which atom it is. Like in this case, we're talking 3 positives, 3 protons. I mean, this whole thing is lithium, but they do not have any effect whatsoever on the bonding. Okay. And another big key to point out is that elements will not just gain or lose electrons. There has to be a second atom involved in this whole process. They are either taking electrons from another atom, or they're giving electrons to another atom. Okay? So there has to be at least a give and take. It's not like there is a magical bucket of electrons somewhere that fluorine's going to say, hey, I want an electron, and just go take from the bucket. Fluorine has to find something that is willing to give up 1 electron in order for it to become happy. Okay? And we'll talk about that a little more when we get into the bonding pattern specifically. Now, because we've got at least 2 atoms involved, we have multiple types of bonding patterns. We're generally going to stick with binary compounds. A binary compound means that there are only 2 elements in it. Like NaCl has just sodium and chlorine. Like CaCl has calcium and chlorine. Like potassium sulfide has potassium and sulfide. Okay, so realistically, we've only got 2 different elements involved in the bond, which means that we have a binary compound. And again, your root word is bi, so you should be able to kind of keep track of that. When we talk about bonds, we're going to focus on 2 different types of bonds today, and it's actually going to be to the point that I'm going to split up the video into 2 different parts. Today is going to be based solely on ionic, and then our second video will be kind of looking at the covalent a little bit. All right. So what we're going to look at is how we can have atoms interact and bond together. That's our key today. And hopefully you remember that when we have 2 things bond together, you're going to end up with a compound that happens to have new chemical properties. Okay, so the things that bind together are going to be different than what the original 2 elements were in terms of melting points, boiling points, brittleness, luminosity, effects with oxygen, effects with water, stuff like that. Okay. Anyway, so we're going to spend the day and we're going to zoom in on our ionic compounds. So starting off, an ionic bond is going to be a bond that is formed when 1 atom gains an electron and 1 atom loses an electron. And another way that I like to think of that is I like to call that transferring electrons. You're basically giving an electron away. So if we look at this example here, we started off with lithium because it had 3 electrons. 1, 2, and 3. And this guy over here was 1, 2, 3, 4, 5, 6, 7, 8, 9. Being that it was 9, this guy was a fluorine over here. Fluorine with 9 electrons and 3 electrons. Realistically, what happened here, though, is having this 3rd electron made lithium really unhappy. It had only 1 in its valence shell, and it said, I don't want 1, that makes me a little more unstable. I would rather just have a complete ring on the inner side, a complete orbital. And so if I can get rid of this, if I can find something to get rid of this with, that would make me happy. Fluorine, on the other hand, went through and said the same thing. It had 7 valence electrons. Okay? And with its 7 valence electrons, it was so incredibly close to being happy and stable, just like the noble gases, with 8 valence electrons. And so when these two got together, got in proximity of each other, this outer shell, this third electron, ended up just being transferred over to the fluorine. And what that does is that causes a change in the charges. Because we gained an electron here, this now becomes F minus, and the lithium becomes a Li plus. And as you remember from way long ago, the opposites, Li plus and F minus, are actually going to attract each other. And that's what causes the strength of an ionic bond, is the fact that you have opposites attracting each other after that electron is transferred. Okay. A big key here is that these are always happening between a metal and a non-metal, and between two oppositely charged ions. So realistically, you should remember that we happen to have our cation, which is going to be positive. And if you picked up anything from the last slide, you should pick up that this happens to be the metal. The metal is going to lose an electron and become positive. On the other hand, you happen to have an anion, which is going to be negatively charged. And that guy is going to end up being our nonmetal. So because we've got two oppositely charged atoms, we know that one has to be a metal and the other has to be a nonmetal. Okay? And so your ionic bonds always occur between your metal and nonmetal. And when we go through and we have this bonding occur, another key point about this is that the product is always going to end up being neutral. And the neutral is very important. And basically what that means is that the oxidation numbers add up to 0. And we'll look at how that works with some examples in a second. But your double check is, do the oxidation numbers add up to 0? If they don't, you definitely did it wrong. So that's your easy double check. So what we're going to do is we are going to practice a couple examples real quick. And we're going to start off with NaCl, but we'll work our way through to a couple other examples. So we basically have 3 steps in determining an ionic bond. First step, figure out the oxidation numbers. And when we go through and we figure out the oxidation numbers, we know that Na happens to be a +1 and Cl is a -1. And you should remember that from the last set of notes we did. Second thing we are doing is we are drawing the Lewis dot structure for each atom. So for those of you guys following along at home, it's going to end up with a Na with a singular valence electron and Cl with 7 valence electrons. And realistically, what I like to do when I'm setting these up, because it'll make my life easier and it'll help you out visually, is I like going through and actually setting them up so that the open valence electron kind of matches up. We know that those two are paired, those two are paired, those two are paired, but this is a lone electron on the side of chlorine. Well, this is a lone electron on the side of sodium, and so getting them paired up by each other will make your life easier with the drawing. The third step is we need to go through and draw the electrons actually being transferred in the proper direction. So for our sodium here, where we've got a Na with a singular electron, what we're basically doing is we're going to take this electron, you're just going to draw an arrow to right there. Okay? And don't forget that there was that 1 electron there. Now I'm not going through and actually drawing the 4th or the 8th electron over here. Right? But when that transfers, your sodium becomes positive, your chlorine becomes negative, and they happen to attract each other because that opposites attract. Okay? Now there is a double check for this whole thing. Your double check is, does each atom have a full valence orbital? When this sodium went through and lost an electron, it kicked down to the lower energy level that happened to be the 2s and 2p orbital, and that happens to be full. And the chlorine gaining its 1 electron ended up bringing its 7 to a full outer valence shell of 8, making both of those very happy. All right. So let's go ahead and try out a couple more of those. And NaCl was our really simple one. But let's go through and try out something like, forget NaCl, CaCl. Okay. So for CaCl, the first thing we want to do is find the oxidation numbers. So I know my calcium happens to be a +2, and my chlorine happens to be a -1. Now here's an awesome trick in terms of figuring out how many of each atom you need. Remember, we need this to be a neutral atom. the way I could go about this is I could think, what's the lowest common denominator of both of these? It's 2, so I need to make sure that I've got 2 CLs. That's awesome. Another quick way is there's a real good trick here. If you just go through and crisscross, you'll end up with Ca1, Cl2. And of course that Ca1, the 1 is invisible, so we never show that, so that really just turns into CaCl2. Okay? So when we draw out our structure, I know that because I've got 1 Ca and 2 Cls, I'm going to throw that Ca in the middle with 2 valence electrons. I'm going to go through and I'm going to draw a Cl over here with 1, 2, 3, 4, 5, 6, 7. Remember to line up the open sides. I'm going to go ahead and draw the Cl over here with 7 valence electrons. And what's going to happen is I'm going to transfer my electron here. I'm going to transfer the electron from calcium to chlorine over here. Please remember to make sure the arrows are going in the correct direction. Okay? So our final structure should look a heck of a lot like this guy. Okay? And when we get all said and done with that, this is going to be a negatively charged chlorine, this is going to be a negatively charged chlorine, and this calcium will turn into a +2 charge because it lost 2 electrons in the process. Alright? So hopefully the drawings make sense. Obviously if we go through and we do stuff transferring inward, that's totally possible. We can do stuff that happens to be like a potassium oxide would end up being K2O, and in the case of K2O, I set up my oxygen, 1, 2, 3, 4, 5, 6. I got a potassium here, and I've got a potassium here. And basically this guy's getting transferred right there, and that guy's getting transferred right there. So the order or the direction of the arrows is massively important depending on what's receiving and what's losing electrons. Anyway, so moving on, when we talk about ionic bonds, we obviously have some properties involved. We remember that when we form a new compound, basically they have different properties, and we've talked about this with salt before. Sodium by itself is an explosive metal that or a very reactive metal that happens to burn when it comes in contact with water, and chlorine gas is a poisonous gas that was the basis of mustard seed, or it's not mustard seed, mustard gas. Okay. When they combine together, however, they form table salt, which is neither reactive with water nor a poisonous gas. It makes my French fries delicious. So the properties will change when you take 2 atoms and bond them together. Okay? And so properties that we generally see with ionic compounds, they happen to have stronger bonds, and that's because of your positive and your negative, your opposite charges attracting. Because of those strong bonds, they happen to have very high melting points and higher boiling points. Okay. They happen to conduct electricity very well when they're in solution or in a molten state, and basically what that means is if you happen to have salt water, it's going to conduct electricity better than distilled water would. And most ionic compounds happen to be a crystalline solid at room temperature. Okay, and we'll go through later this week and we'll try to actually take some unknowns, and you're going to determine whether we're ionic or covalent unknowns based on the properties. So these are things that we'll use in class. Anyways, hopefully that goes through and wraps up the idea of ionic compounds. The next video itself is going to talk about covalent compounds. So we'll start that up in just a second.